acids, what they are molecules. And now molecules are a specific type of connectivity. Anyone remember what kind of bonds they have? Covalent. So typically when we learned about last unit, we talked about electrolytes, we talked about ionic compounds. Acids are the exception to covalently bound compounds that have ions that form when you dissolve in water. So this makes them electrolytes. So these are the exceptions. So acids are electrolytes because they have an H plus ion that leaves the acid. And what ends up happening is we make what's called the hydronium ion, which is H3O plus. So I'll write that down for you here. Apple pencil. There we go. So this is called the hydronium ion. So it's a positively charged molecule. And so I'll show you kind of how this works. So we're first working with HCl or hydrochloric acid. And so when you dissolve that in water, this hydrogen of the acid gets donated. So it ends up becoming that hydronium H3O plus aqueous. And then you're just left over with the anion, the chlorine -1 ion here. So as you can see, when it dissolves in water, it forms charged ions, therefore is an electrolyte. And so if we do this now with sulfuric acid, we now have 2 hydrogens that are able to be donated. So we are going to make 2 moles of hydronium ions then per 1 mole of sulfuric acid. So you end up making 2 moles of H3O plus, and then you have a SO4 sulfate ion -2. Both of these are aqueous. What if I had phosphoric acid here? How many moles of hydronium ions do you think we could make? 3. So this all depends on the number of hydrogens that the molecule has to be able to donate. So it will change the number of moles we can make. Any questions about this? Pretty much biggest thing to know is that an acid is an acid if it donates an H plus and makes the H3O plus ion. Any questions about that? Cool. So kind of breaking down a little bit of the Lewis structure of what this looks like. It's not the most straightforward, but if you have a hydrogen, and let's just use HCl as our example. So hydrogen has 1 valence electron, chlorine has 7. This is how they would be shown bonded to each other in a Lewis dot structure. What ends up forming is you get a H plus molecule. So remember we use brackets and then the charge. And that electron that came from hydrogen stays with the chlorine. So these are the 2 ions that they make. They make the H plus and the Cl minus. As this H plus is just moving along in water, doing its own thing, it decides that it wants to hang out with a water molecule. So I'll draw one of those real quick. So remembering that water has 6, or oxygen has 6 valence electrons. And then there's 2 hydrogens already bonded to it. So it seems weird because you're like, wait a second, there's not really anywhere for the hydrogen to go. But that negatively charged oxygen has enough pull to make what's called the coordinate covalent bond with the hydrogen from the acid. So what we end up having is our hydronium. Hydrogen just kind of hangs out there on one of the lone pairs. And then this whole thing gets a charge of +1. And now it's not super important that you guys understand what happens. I just kind of wanted to give you a little bit more background on how this weird H3O plus forms. Any question? So don't worry about memorizing the mechanism. Okay, let's talk about some cool things that acids do. Well, they like to oxidize. So this is something that we've talked about before. And so they oxidize active metals or eat them away. So things like lithium, magnesium, zinc, these are super common metals that are oxidized. And in turn, they produce hydrogen gas. So how we decide if something is what we call an active metal or able to be oxidized has to do with this activity series. So this is table J in your blue packet. I also put it on the right-hand side of your notes here. Highlight where H2 lives. So this is where hydrogen gas lives. Anything that is above H2 will be oxidized. Versus anything below won't oxidize from acids. So it has to be above this H2 mark. Any questions about that? So just some examples of what these things look like. So if we have lithium that combines with hydrochloric acid, we create lithium chloride in that hydrogen gas. And so remember, oxidation, remember oil rig? What does the oil stand for? It's losing. So it's losing electrons, therefore becoming more positive, right? Well, elemental is 0 as their charge, their oxidation state. What is the charge of a chlorine ion? -1, right? So what does this make this lithium? +1. So this is showing, yep, it actually was oxidized by the acid. Same thing for the one below, except calcium goes from 0 to what charge? +2, exactly, because there's 2 chlorines there, both with the -1 charge. So in order to be neutral, it has to be +2. So this is just showing how the acid oxidizes the metals. Talking about a pH scale, so again, this should be somewhat familiar, but acids have a pH that's less than 7. But I want you to also note, the closer you are to having a pH of 1, the more acidic you are, the stronger the acid. And so the pH scale isn't only just for acidity, but it's also for what's called alkalinity. So anytime you guys see alkaline or alkalinity, this means being a base. So it's just another term we use for bases. What is the pH if you're neutral? 7. So at 7, you're neutral. Anything less is acidic. And one thing I want to emphasize too, which I feel like isn't very obvious, but each pH value is a tenfold of difference. Meaning, if you have an acid that's a pH of 5, and you compare that to an acid that's a pH of 4, the pH 4 acid is 10 times as strong of an acid than pH of 5. So it's a big magnitude of difference, and the scale works all through the powers of 10. As you probably could assume for number 3, yes, acidic solutions conduct electricity, but strong acids, they are strong electrolytes. So they really like to make those ions. And then weak acids are weak electrolytes. So nothing too tricky about that. One of my favorite fun facts is that solutions of acids are sour. So rest in peace to whoever figured that out for us. But we know this. Does anyone like salt and vinegar chips? Yeah, vinegar is just a dilute solution of acetic acid. So you're literally eating acid for enjoyment. So it's just funny that we figured this out and actually something that a lot of us like to enjoy. And then lastly, anyone make a baking soda and vinegar volcano before? Here's the equation for it. What happens is that if you add baking soda with vinegar, vinegar being the acid, you're actually going to form carbon dioxide vapor and water vapor. So that's the bubbles that you see happening, and then a salt. So honestly, I'm trying to think of what would be in the Mentos. There's plenty of acids in Coke. I'm telling you, I'll just hide that. But I'm actually unsure. I haven't ever actually done that reaction. We should do it sometime. Okay. All right. All right. So in reference table K that you guys have in your blue packet, this will give you names of very common ones. So there aren't names of every type of acid in there, but the most common ones, kind of for reference, are listed there. And we'll talk about how they name these things. But one thing I want to note, just so you guys aren't weirded out, there is just aqueous CO2 listed as part of carbonic acid. But I want you guys to know that in the oceans, in any water system, there's this delicate relationship of equilibrium that happens, and you don't necessarily have to write this down. I just want to tell you about it. But there's this delicate relationship between carbon dioxide and carbonic acid. So this has to do with the levels of pH depend on how much carbon dioxide is in our ocean systems, which depends on our climate, which is changing because of climate change. And so like a lot of things that happen, why systems can't survive the same way, has to do with how much carbon dioxide is able to be dissolved in our waters. Because as we know, the temperature affects how much gas can dissolve. So I'm just saying, don't get weirded out that there is a non-hydrogen containing compound in with these, but the reason being is the second it goes in the water, it starts messing with things and kind of adds to this equilibrium here. And then just for acetic acid, it's written different ways depending on if you're writing it. So sometimes people write it like this bottom one, it gives a hint on what its structure looks like. So it's the same thing. Just it's telling you that you have a methyl group. So here's my CH3 connected with a carbon that's connected to an OH and double bond to an oxygen. So this is acetic acid, which is the same thing as vinegar. Okay, how do we name binary acids? So these ones aren't too bad. We give a prefix of hydro for hydrogen. And then what we do is change our ion name. Oops, non-mental, that's a good one. Non-metal ion name with the last syllable. So typically we have chloride, fluoride. We change that "ide" to the suffix "ic." So what we did have before as our chloride becomes our chloric. And so we put that prefix then we have hydrochloric. Do we have a question?
Yeah, so I do actually. So is hydrochloric with fluoride? Yes.
I did not believe that.
So if we have bromide, it's going to be bromic. And so hydrobromic. Lastly, nitride. We change that "ide" to "ic," nitric. And then we have hydronitric. And then all of these can be followed up with the word acid. Any questions on binary? So this is when you only have two elements present. Okay. So if you were given the name, it's the same kind of practice as we've had before, where we always put our cation first. But what is our cation in every single one of these now? Hydrogen. That's our positive. So we always are going to write our hydrogen first and our anion second. So hydrofluoric will be hydrogen and fluorine. Hydrophosphoric is going to be hydrogen 3 and then phosphorus. So the reason being is you have to remember that the different ions form different charges. Phosphide has a -3, so you need one hydrogen for every charge there. Any questions about writing formulas? Okay, now we're going to talk about ternary acids. So when it's not just two elements, but there are acids that are made from polyatomic ions. So table E is not going away quite yet. So with polyatomic ions, this is a fun one to say. I sound like Dr. Seuss here. So if the suffix is ic, or the suffix will be ic if the ion ends in ite or ate, and the suffix will be us if the ion ends in ite. So we have things like sulfate, sulfite. They're going to have different endings that happen. And so pretty much we're dropping the prefix hydro and naming them based off of the polyatomic ion and then adding the word acid. So I think it's easier to just pick out the polyatomic ion. So if we look here, this is chlorate. So if we look at 8 gets the ending of ic. So this now becomes chloric. And then we just add the word acid and we're done. Chloric acid. So they're just named strictly off of the polyatomic. It's assumed that we have hydrogen here. Now, when we have chlorite, this becomes chlorous acid. So ite gets OUS. And then lastly, cyanide. That also the IDE gets ic, so it's cyanic acid. Any questions about writing them for polyatomics? So this is going to be really digging into table E and being able to recognize these things. I think it's a little bit harder to go from the name to the formula. I just grabbed a couple easier examples here, but if you have sulfuric, what ending are we going to have for our polyatomic ion then? Ite or ate. And so if you looked at your table, you'd see sulfate, and you know sulfate is an SO4 minus 2. So in order for it to be an acid, we add as many hydrogens as the charge here. So our final formula would be H2SO4. Versus when we have the ending OUS, that's going to be ite. So sulfite you'd find on the table E here as SO32 minus, still adding a hydrogen for your charge. These would be the formulas for both of those acids. Any questions here? Julio. Let's talk about bases. Talk about what it takes to be basic. There's so many jokes that I will keep to myself throughout this lecture. So bases. Now this is a specific type of definition. So you can describe bases in different ways. Different people are like, no, this is what I think is a base. But this is specifically Arrhenius. I'm going to make sure I spell this guy's name right here. So this definition is Arrhenius. So what this guy said is a base is a substance that contains hydroxide ions, so OH minus. That's one of our polyatomics. You guys need to really solidify. Hydroxide is OH minus, and hydronium is H3O plus. Those are things I expect you guys to know. And again, I want to make sure that you guys get used to this word because I'm not sure if you've used it before, but another way to describe bases is alkaline. And so here, this is the table. I think this is table K. No. What comes after K? L, table L in your packets. This is just a few common bases here. And so what's really nice about naming these is ionic rules, except we already know the anion is hydroxide. That's our negative. So we just have to list the metal and then hydroxide. So sodium hydroxide, potassium hydroxide. So they're not too bad. And then ammonium hydroxide is the special one that has 2 polyatomic ions there. So the namings aren't much different than what we are used to for ionic. Now the properties that they have, bases now have a pH that is greater than 7. They also conduct electricity because a lot of these are ionic compounds. We know this already. Any guesses on how bases taste? Bitter. They taste bitter. And then they can be formed with our group 1 and 2 metals that react with water. So just the metals reacting with water is enough to create a basic solution. So what ends up happening is we kind of have this trade-off where our metal will then bond to a hydroxide. But how many hydroxides does magnesium need? What's magnesium's charge? Yes, magnesium is +2, so we need to write that it gets 2 hydroxides. And then we're always making that hydrogen gas as well. So this is just the addition of putting metal in water. So how do we know if a solution is acidic or basic? I could go into depth on how pH probes work. It's actually quite fascinating. People are too smart. But really just as a basis of detecting the electrical conductivity from these ions, how much electricity can they actually transfer? And that'll give us an indication of their pH. What we're going to be using in our lab for titration are acid-base indicators. So they're not as analytical, but they have a characteristic color that depends on the pH. And when I tell you guys, it can take like a quarter of a drop of acid to change the color of an indicator. It's pretty cool use to see, like at one point the solution hits kind of, there's like an equilibrium here, which we'll get into in a few units. So we'll be using those to monitor our pHs of our lab. And so table M, what it does is it goes through different indicators. So we have different indicators because their range that they can detect color depends on what their compound is. And so like methyl orange is really good if you're shooting for a pH between 3.1 and 4.4. It can tell you where you're at. So how to use this chart is things that are 3.1 and below are going to be red. Things that are 4.4 and above are going to be yellow. So in between, it's going to kind of have a nice orange color versus bromothymol blue will be yellow at below 6. So I just read it kind of left to right. Yeah.
So if something is like more sour than something else, that means it's more.
That's a good question. I have no idea. And then the one that we're going to be working with for our lab is phenolphthalein. So phenolphthalein, this is one of those words here I laugh because I know how to spell this, no problem, but I can't spell words like bicycle. But this is one that goes colorless until it hits pHs of 9. So it's pretty cool. You'll have a clear solution and all of a sudden it'll be bright pink. Let's say you guys tested a solution, trying to figure out its pH, and these are your results. When you tested it with the indicator methyl orange, it was yellow. Phenolphthalein, it's colorless. Bromocressyl blue, thymol blue is yellow. So what we're gonna have to use is use this table to try to kind of figure this out. So if we know that with methyl orange, it's yellow. If this is where it's yellow, do you think the pH is above or below 4.4? Above. So I'm going to make the note here that it's yellow, so it's above 4.4 pH. So that means we can cross out A. Now with phenolphthalein, it's colorless. So that means it's got to be less than 9 because 9 is where it hits pink. So it's less than 9. Nothing's above 9, so we can't cross out another option. If we tested it with bromocressyl green and it's blue, it's going to be above this 5.4 then because it goes yellow to blue. So if it's above a pH of 5.4, we can cross out D. And then lastly, thymol blue is yellow. So if we look at that, it is yellow at pHs less than 8. So that means it has to be less than 8. We can get rid of option C. So it must have a pH, it could have a pH of 6.5.